Today we are going to understand about some of the properties of recursive language and recursive enumerable language, some of the theorems. I'm your instructor Poonam Patel. Let's start to understand this concept. Now, before we are going to discuss about some of the theorems, first discuss about the recursive language. As we know, what is a recursive language? Suppose a language L is called a recursive if it is accepted by a some Turing machine M, which is denoted by L of M, such that if a string W is in L, Turing machine M accepts it and then holds. If the string is not in L, then M eventually halts, although it never went to one, it never enters on accepting state, but it enters on a non-final state. It means that it enters on a rejecting state. So we can say that Turing machine will always halt for the recursive language. So it means that if we have a language and we construct a Turing machines for it, suppose it is in a recursive language and we can construct a Turing machine for it. So a Turing machine for this language, so here you can see we can also call a recursive language as a definite language, or the language which can be represented by some algorithm, and such algorithms helps in a constructions of Turing machine for that language. So we can say that, so if we design a Turing machine for the language, so this is my Turing machine M, and here I give a input string W, suppose. So for the recursive language, what's happened? If W is in language, the Turing machine will always halt and accept it, okay, accept it. But if the string is not belongs to L, so what happened? So Turing machine also halt, but in a rejecting state. It means that it halts on a non-final state. So here we can say that reject. So Turing machine will always reject that strings. We can say that. Okay. So here we can say that the accepting state and rejection state both are properly defined for the recursive language. In case of recursive enumerable, accepting state is properly defined, but rejecting state is not a properly defined. The Turing machine may enters on an infinite loop or may enter in a rejecting state. Now, next, what is the decidable language and undecidable language that we have already studied? So here we take some summary about this languages. So if a language is recursive, then it is called as a decidable language, and if the language is not recursive, such a language, we can say that it is an undecidable language. So we can broadly classify three categories of languages: recursive language, recursive enumerable language, and non-recursive language, non-recursive enumerable language. So recursive language for which the algorithm exists, recursive enumerable language for which it is not sure that on which input TM will ever halt, and such language are not a recursive, and the non-recursive enumerable language for which there is no Turing machine, there is no Turing machine at all. The non-recursive enumerable language for which there is no Turing machine at all. So here I have defined the relationship between these three class of languages. This figure shows the relationship between these three class of languages: recursive language, recursive enumerable language, and outer portion is not recursive enumerable language. Here you can see this portion recursive is a, we can say that recursive is always subset of recursive enumerable languages. This E for enumerable languages. So here you can see, and this highlighted portion shows that this portion shows that this is not a recursive, some of the portion which is not a recursive in a recursive enumerable language. Now we are discussing about some of the theorems which we can say the properties of recursive language and some of the properties of recursive enumerable language. So first theorem said that if the L is a recursive language, then its complement L dash is also a recursive language. Let us understand this concept by using the proof. So here I have construct the halting machine. Here I have construct the Turing machine which accept the L dash. We can say that. So here suppose Tm. So here you can see this is M, which represent the which is a Turing machine is designed for the language L, and M dash is represent the complement of that language. M dash represent the Turing machine which designed for the complement of language. So here we can say that suppose Tm Turing machine M, this M is accept the language L. So we can say that this is a recursive language. It means that it always halt either in accepting state or in rejecting state. Now we can construct the new Turing machine which is the complement of that which is a complement of Turing machine M. So here you can see this figure is shown that like this. So suppose this is my Turing machine M which accept the language L, okay, and this is my Turing machine M dash which I can say complement of Turing machine M. It means that which accept the complement of language L. So if you see, if I given an input string W for this language, so either this is a recursive language, this is a recursive language, this is a Turing machine designed for recursive. So either it if W is in a language, it accept it. If it is not in a language, Turing machine is rejected. Now turn around now move on the complement. So complement means that if this machine is accepted, so it complement is always rejected, and if this Turing machine reject the string, it means that this complement is always accepted because it's complement. So when the Turing machine M will accept it, M dash will always reject this, will always halt on a rejecting state, and if M will accept this, M will reject the string, M dash will always accept that string. So we can say that there are two state is properly defined for that L dash also. So we can say that this two state is properly defined for the M dash, which is represent the complement of L Turing machine. So M dash is the Turing machine for which is designed for the L dash. So these two states are properly defined. So we can say that this L dash is a recursive language. Always remember, whenever we have designed a Turing machine for the language, and in a Turing machine, if the two state, accepting state and a rejecting state, are properly defined, we can say that this language is a recursive language. Now move on the next theorem. Next theorem said that if L and L dash, next theorem said that if a language L and its complement, theorem 2, if language L and its complement L dash both are recursive enumerable. So here RE means that recursive enumerable language, then this L is called as a recursive language. So here I have a, so now let us understand how it is possible. So let us understand this concept. Okay, so consider a Turing machine which made of a two Turing machine. So here they are talking about the two Turing machine L and L dash, and this M is made up of this two Turing machine which accept the L and L dash. So here this two Turing machine is denoted by M and M1. M1 is represent the language L, and M2 is the complement of that language. So here M1 is a Turing machine which is designed for the accepting language L. M2 is a Turing machine which is designed for the complement of. So here the machine M2 is the complement of machine M2, which is a Turing machine which is the complement of M1. So we can also denoted that the Turing machine L is equal to L of n, which accept the language L, and M2 machine which accept the language L dash, which is a complement of L. Now here you can see in this figure I have simulated this machine in parallel by machine M. So here I have constructed a machine M which is a simulated this two machine parallelly. It means that here I have given, it means that this machine has a two tap machines where one tap is simulated to a M1 and the other tap, this other tap is simulated to M2. So now these two machines are recursive enumerable language. It means that accepting state are properly defined, we can say that. Now, so here we can see if the string is in M1, it will accept it, so M will eventually halt on accepting. If the string is not in L, it means that it is in an L dash, it means that M2 will accept it. When M2 accepted, M halts without an accepting state, and we can say that on all input M will eventually halt and it behaves exactly like a M1. So we can say that L is a recursive language. Is a closure property for the recursive language. They said that the theorem 3 said that the recursive language are closed with the respective to the union. It means that if I have a two languages L1 and L2, both are recursive language, and if I perform on a union on these two languages, the resultant language will always a recursive language. Now let us understand this concept by using this proof. So here so here you can see in this figure, you can see I have taken a two machines M1 and M2. M1 represent the language L1 Turing machine. So M1 is a Turing machine which represent the language L1 and M2 is a Turing machine which represent the language L2. So we can denote this thing. So we can denote this thing L1 equal to L of M1, L2 equal to L of M2. Now both are the recursive language. It means that M1 will always halt, M2 will always halt. Now if you see, I have designed a machine M which is a union of these two languages. So as we know, union, it means that the resultant language, so we can say that. So suppose L1 union L2. So suppose L1 represent the language which contain the string starting with A. L2 is represent the language. L2 is a language which contain a strings which starting with B. So if I perform a union on this two languages, so what L contains? So L contains the string which starting with A or a starting with B. So either a string which start with A, it also accepted, or the string which belongs, so we can say that the string which belongs to L1, L is also accepted, or the string belongs to L2 is also accepted. So here you can see, if I have given an input string W to a machine M1 which represent the language L1, so if the W is in L1, it accept it, and the union and it accepted, so this M is also accepted either in L1 or L2, both are accepted. So here you can see, so our machine M will accept it. Now if the string is not in M1, if string is not in M1, let me check whether the string is, we can check whether the string is M2 or not. So we can give the input to the machine M2. So if the string is in M2, it will accept it, and the machine is also M accept it, and if the string is not in M2, it reject it, so the machine M is also rejected. So here you can see accept and reject both are properly defined. So we can say that this union, after performing a union on these two languages, the resultant language is also recursive language. Now last theorem, which is the intersection. So if I perform a so the recursive language are closed with respect to a intersection. So if L1 and L2 are recursive language, then so the resultant language L is also a recursive language. So here I have given a proof. Here you can see. Let me understand the figure. So here you can see. So M1 is a Turing machine which represent the language L1, and M2 is a Turing machine which representing L2. So if the string here and this N is a resultant Turing machine which is designed after performing an intersection on these two languages. So intersection means, so the string which belongs to in both this two languages, it accept it, otherwise it will reject it. So here you can see W is given to a, suppose an input string is belongs to M1. It means that this machine is accepted. So if this machine is accepted, this input is given to also M2. Let me this input is given to a machine M2. So if the string is in M2, if the string is L2, if the string is in L2, it accepted. So the intersections, so this machine M1 also accepted. But if the M1, so if this string is not in L1, it means that it directly rejected, and so this M is also rejected. So if the string is in M1, it means that it accepted. So there are two possibilities for the machine 2, either it accepted or rejected. So if the string is not in M2, it means not in L2, it means that the machine 2 will reject it, and the machine M is also rejected. So the problems basically divided into two groups. The first group, which consists of problems that can be solved in a polynomial time. Example for this group is like searching an element from the given list, which takes the time complexity O log of n, we can say that. The second group, which consists of problems that can be solved in a non-deterministic polynomial time. The example of this group is like a knapsack problem, traveling salesman problem. Now, any problem for which answer is yes or no, we can consider as a decision problem, and the algorithm for this kind of problem is called as a decision algorithm. And we can say that any problem that involves an optimization, like we have to find the minimum cost, what is the minimum cost for this path, what is the maximum cost for this path. So this kind of problem is considered as a optimization problem, and the algorithm for optimization is considered as a optimization algorithms. Now, as we know, the problems are divided into two main categories: the class P problems, NP class, which again divided into NP complete and NP hard. Now start with the class P problems. So the problems with at least one algorithm that solves the problem in a polynomial time with respect to, we can say that, input side. So we can say that class P problems means the problems that can be solved in a polynomial time. If we consider the class P problem with respect to Turing machine, so the problem which can be solved using a deterministic Turing machine, we can say that this problems is belong to a class P problems. So what are the example of class P problems? So here the minimum weight spanning tree. So given a connected weighted graph, and we have to find a minimum weighted spanning tree. The example for this is a Kruskal algorithms. So as you have already studied about this concept, minimum weighted spanning tree. So this minimum weighted spanning tree, basically this problem is belong to the class P problems. So it's an algorithm which solves this problem in a polynomial time. Example for this is Kruskal algorithms. NP class problems. So the problems that can be solved, we can in an exponential time, like non-deterministic polynomial time. We can say that this problems belong to NP class problem. If we consider as a with respect to a Turing machine, so the problem which can be solved in a polynomial time using a non-deterministic Turing machine belongs to the NP class problems. Example of NP class problem is traveling salesman problem. Suppose a given number of cities and the cost of traveling from one city to other cities, and what is the cheapest round trip route Route. What is the cheapest round trip route that visit each and every city exactly once and then returns to the starting point. Return to the starting point. So given a number of cities and the cost of traveling from any city to other city is given. Now what is the cheapest round trip route? What is the cheapest round trip route that visits each and every city exactly once and then return to the starting city? So there is no one algorithm which solve this problem in a polynomial time. So the only way to solve this problem, we have to consider the number of possible paths and checking them one by one. Now next is NP complete. We can say that a problem D is called a NP complete if it belongs to a class NP and every problem in NP and also to be solved in a polynomial time. If NP had problems that can be solved in a polynomial time, then all NP completes also be solved in a polynomial time. The NP class problem are the decision problems that can be solved by a non-deterministic polynomial algorithm. So I hope this concept is clear to you. Thank you all.